Okay, so we were talking about tensor localization, and we proved localization, the uniqueness of localization of a ring at a certain multiplicative set. So, we said last time we showed that S is a multiplicative set in A, then the set S inverse A is uniquely determined by three properties. What are the three properties? There exists a map f from A to S inverse A, sending f of A to A by 1 such that for every S belongs to S, Fs is a unit in S inverse A. Then second property, f of A is 0 implies there exists u in S such that u A is 0, and the third property is every element of S inverse A is of the form f A times f S inverse, right. So, the localization, this ring is called localization of A with respect to the multiplicative set S. Okay. Let us look at some interesting properties of more properties of S inverse A. This is one of the most important applications of S inverse A, that if I take a prime ideal, be a prime ideal, okay, and if I take S to be A without P, then 1 belongs to S, right, and if A and B are in S, A B is also in S, right, because if A B is in S, if A B is not in S, that means it will be in P, but P is a prime ideal, therefore, either A is in P or B is in P, or in other words either A is not in S or B is not in S. So, therefore, this is a multiplicative set it is a multiplicative set, and one can talk about S inverse A. So, S inverse A, this is also denoted by AP, A localized P. So, this is a very important ring, localization at prime ideals. Okay. One instance that I can immediately talk about is, suppose I take a prime ideal in, so let K be a field and P be a prime ideal. Prime ideal in K x 1 up to x n. Okay. Take V to be the variety of P. What does that mean? V is all n tuples in Kn such that f of A1 up to An is 0 for all f in P. I look at all the elements of P and look at all the points in Kn which vanish on this one. So, let us look at a simple example. I take the prime ideal, I take the ideal x square plus y square minus 1 in R x comma y. Okay. Can you tell me what are the elements in R2 such that variety correspond? Okay. So, and I look at this ideal, this ideal. What are the elements in R2? So, this is a prime ideal. This is an irreducible element. There are some one needs to prove this. This is an irreducible element, and it this is a PID? It's a UFD. Okay. So, therefore, this is prime, and therefore, this is, if this is prime, it is a prime ideal. The ideal generated by this is a prime ideal. Now, what is V corresponding to this? Can you imagine that? I am looking at all points A comma B in R2 such that A square plus B square minus 1 is 0, or in other words all AB such that A square plus B square is 1, which is the unit circle. We call it S1. Okay. So, these are all algebraic sets, or these are all called the varieties. Okay. In algebraic geometry, what one does is, given algebraic sets, one has to study lot of properties of this algebraic set, geometric properties. So, the idea is create corresponding algebraic objects, study algebraically, and take the properties back into the geometry. Okay. So, one of the such objects is the correspondence between V and P. Okay. Now, if I look at, so here V is, in this case V is S1 in R2. Now, coming back to the general case, the ring, so I call this ring to be A. Okay. The ring AP here is set of all f by G such that G is not in P, right. That is by definition. I am looking at S inverse A localized at P is S inverse A, and S is A minus P. So, this is by definition set of all f by G where G is not in P. G is not in P is equivalent to saying that G does not vanish on all the points of V. Okay. So, or in other words, as a ring of rational functions from Kn to K, this is regular, this is a well defined continuous function, because this does not have any zeros, this is nowhere vanishing, right. G is nowhere vanishing on V. So, therefore, this is AP is set of all, it is called a ring of regular functions on V. Okay. And this ring plays an important role in algebraic geometry in the study of varieties. So, this is one such occasion that one encounters in the as applications of this localization. So, this is one of the most important objects. There is more, this is there is more closer study that if you take local ring corresponding to a point, you can further take what is called a ring of regular functions which are at a point, local ring corresponding to points in a variety. We will not get into that. You will certainly see that if you opt to take algebraic geometry course in the next semester. Okay. So, let us get back to this. So, this is one of the important applications of localization in. Okay. So, now let us look at this ring in general. So, this is A is k exponent x n and p is prime ideal and so on. Let us get back to another remark. In general, suppose I take P be, let P be a prime ideal in a ring A. So, I am not saying that A is k exponent x n. This is in general A be a commutative ring with identity and P be a prime ideal. And consider A P. Okay. Take an element in A localized at P. So, let x by S is in A localized at P. See, if x is not in P, if x or okay, let us take if x is in P, can this be a unit? If x is in P, x by S cannot be a unit, right? X by S is not a unit. Why is this not a unit? For this to be a unit, I need an element, let us say y by S such that y by t such that x by S by y by t, this is 1 by 1. Or in other words, what does this mean?
This will imply that S is a unit, which will imply that P is not
Why is x a unit?
ST will be
This will say that there exists t in so u in S such that xy minus st times u is 0, right. What does this say? xyu is stu. Now, u is not in P. See this, so okay. See, this is an element xyu. xyu is not in P because it is in S. Look at the right hand side, it is stu, all of them are in S. Therefore, this is
but X is in P.
x belongs to P implies xyu has to be in P. So, these two, this is one statement, this is another statement, contradiction. So, therefore, this implies x also since x is in P, xyu is in P, therefore, this is a contradiction. Therefore, what does the contradiction say? That x by S is not a unit. That is the assumption that we have made, right. Any element of the form x by S such that x is in P are non-units. Now suppose I take a non-unit, okay. Let x by s in A localized at P be a non-unit. I claim that x is in P. If x is not in P, that implies x is in S, and that would imply S by x is in A P, and that would imply that x by S, S by x, this is 1 by 1, that implies x by S is a unit. So that is again a contradiction. So that means what we have proved now is that any unit in x by S, any unit in AP is of the form x by S, where x is an element of AP. So the set of all non-units, so we have proved that set of all non-units of AP is set of all x by S such that x is in P. Right, we proved both directions. If x is in P, then x by S is a non-unit. Similarly, if x by S is not a unit, then x has to be in P. So we proved that precisely these are the non-units. This can be written as P AP. I will write it as P AP, right, it is of the form P AP. This is an ideal x by S, where x is in P is an ideal. So this set is an ideal. Why is that an ideal? Immediately one can check, 0 is there, it is an abelian group. If A by S is there, then minus A by S is there, then the multiplication with respect to R by S, if x by S and R by T, take R by T in AP, then product is there inside, because that P is an ideal. So therefore this is an ideal. Sorry. So what we have shown is that set of all non-units form an ideal, therefore it has to be the unique maximal ideal. So this implies that PAP is the unique maximal ideal of AP. That means AP is a local ring. That is how the name localization came. We are from A, we have come down to a ring with unique maximal ideal, or you have obtained a local ring. That is why the process is called localization. But you have to be slightly careful with the terminology. S inverse A need not be a local ring for all. So S inverse A need not be a local ring. Okay. I will leave it to you to think about this for the time being. Okay, I can easily give an example where this is not local, but we will study little more properties of localization that will immediately say about ideals here. To start with, suppose let I be an ideal of A. Okay. and look at S inverse I defined this set like this, x by S where x is in I and S in S. This is an ideal.
Sir, why you are taking elements by only like x by s?
Yeah.
Why not summation?
So, what if I take x1 by s1 plus x2 by s2? What is this by definition? s2 x1 plus s1 x2 by s1 s2. Yeah, this is in S, and when we are talking about ideals, this is also there. So, it makes sense. So, this is for the same reason, you can prove that this is an ideal of S inverse A. But now the question is, when will this be if I is a proper ideal, does that mean that S inverse I is a proper ideal? In this case, can you tell me, if I is a proper ideal, when can we say that S inverse I will be a proper ideal? When will it be not a proper ideal? When will it be equal to S inverse A?
Some unit belongs to
S inverse I has to be S inverse A only if a unit belongs to S inverse I. A unit belongs to S inverse I means
some element of S
some element of S
belongs
is in. So, see, any element of S inverse I looks like S by x by S. When can we say that, and here x belongs to I, and we want to say that this will be a unit. For that, what I need is x should be in S as well as in I, or in other words, S intersection I is non-empty, then S inverse I is equal to S inverse A. So, S intersection I is non-empty implies S inverse I is S inverse A. What about converse? Suppose S inverse I is equal to S inverse A. That means I have an element x by S which is a unit in S inverse I, or in other words, so this says that there exists y by t such that x by S times y by t is 1 by 1, or in other words, x y u is equal to S T u. What is that we want to check? We want to see whether x belongs to S. Can we say that x belongs to S? X is in I, y is in I, x y belongs to y. From here, can we say that S inverse I is S intersection I is non-empty?
Yeah, since STU belongs to S,
Yes.
so XYU belongs to S and XYU belongs to I also because it is an ideal.
X belongs to I,
So XYU belongs to I.
x y u. We don't want to say that x is in I. We are not really bothered to say that, right? We only want to say that I intersection S is non-empty. So here x y u belongs to I because x belongs to I, and it is S T u, therefore it belongs to, it is in S. So, therefore, I intersection S is non-empty. So, the converse is also true. So, S inverse I is non-empty if and only if S inverse I is S inverse A. Okay. We will go into the properties little more properties. So, think about now I will give you one exercise to think about. What are the prime ideals of S inverse A? Okay. Think about it. We will come back to that. Now, we talk about localization of modules. We can do the same process. Okay. S be a multiplicative set and M be an A module. Define a relation on M cross S by M S related to M prime S prime if there exists U in S such that U M S prime minus M prime S is 0. The same thing, we are instead of A here we are putting M, no difference at all. This is an equivalence relation. I will again this is an equivalence relation. So, therefore, equivalence relation partition the set and we can look at the set of all equivalence classes. The set of all equivalence classes is denoted by S inverse M naturally, and what do we want to say next? This is a, we want to say this is an S inverse A module, right. So, to start with we need to define an addition on this naturally. M by S, okay, so let M by S denote the equivalence class containing okay. Now define M by S plus M prime by S prime by S prime M plus S M prime by S S prime. Then again first you have to show that this definition is well defined and prove that this is S inverse M is an abelian group with respect to this addition. And define scalar multiplication A by S, A by T times M by S equal to M by S T. So, this then S inverse M is an S inverse A module with respect to this scalar multiplication. we are just going through the same work that we did for S inverse A while proving S inverse A is a ring. So, I am not going to repeat all of them, these are the exactly the same. Here we have slightly less amount of work because it is you only need to prove that it is a module. Okay. So, this gives the localization of M with respect to a multiplicative set. Just to set up a notation, if S is I mean the complement of a prime ideal, then S inverse M is denoted by M localized at P. Suppose I have a map from M to N, let F from M to N be an A module homomorphism. Okay. This be an A module homomorphism. Can you think of this map inducing a map on the localization? Can we think of a map from S inverse M to S inverse N? M by S being mapped to Fm by S. So, this naturally induces a map between. So, I will denote this map by S inverse F. This naturally induces a map from S inverse M to S inverse N. So, therefore, you can immediately ask questions. You have a map F and that induces a map S inverse F. So, therefore, it is natural to ask questions how the properties of F and properties of S inverse F are related. If this is injective, can we say this is injective? If this is surjective, can we say this is surjective? Okay. More generally, suppose I have a exact sequence M prime to M double prime, okay, call this G, call this F. Then corresponding to this I have a sequence S inverse M prime, S inverse M to S inverse M double prime. This is S inverse F and this is S inverse G. Suppose this is exact, can we say this is exact? Right? Natural question. Okay. So, let us try to investigate this. So, our setup is, let S be a multiplicative set and M prime M double prime be A modules such that the sequence is exact. This sequence is exact, therefore, there exists this sequence, there exists an induced sequence, we do not know whether it is exact or not, but let us look at some properties of this. So, I have a map from M prime to M to M double prime. So, I have this composition, right, this is G composite F. Similarly, I have a map S inverse of G composite F. This G composite F induces a map from S inverse m prime to S inverse m double prime, which I denoted as S inverse of G composite F. And at the same time I have S inverse G composite S inverse F coming from composition of these two maps. How are these composition and this map related? Let us take one element m prime by S prime in m prime by S. What is S inverse G composite S inverse F acting on this m prime by S prime? This is S inverse G acting on S inverse F of m prime by S prime, which is S inverse G of, this is, what is the definition? F m dash by S prime, and this by definition is G of F m prime by S prime. But again look at this one, this is G composite F acting on m prime by S prime, but this is nothing but S inverse of G composite F acting on m prime by S prime. So what have we proved? That S inverse of G composite F is S inverse G composite S inverse F. This sequence is exact. What does that mean? Kernel G is equal to image of F, or in other words G composite F is 0. That means G composite F is 0, that means S inverse G composite S inverse F is 0, or in other words image of S inverse F is contained in the kernel of S inverse G. So, image of F is equal to kernel of G implies G composite F is 0, that will imply that S inverse of G composite F, which is S inverse G composite S inverse F, that is 0, and that would imply that image of S inverse F is contained in kernel of S inverse G. The question is whether the reverse inclusion is true. Let us take an element here. Let m by S be in kernel S inverse G. What does that mean? This implies S inverse G acting on this is 0, which is G m by S is 0, right? G m by S is 0, and that implies that there exists U in S such that U is 0. But now U is a ring element, G is an A module homomorphism, therefore G U times G of m is same as G of U m. That means U m is in kernel of G, which is same as image of F. What does that mean? That means there exists some m prime in m prime such that F of m prime is U m. Can you complete it now? The question is whether m by S is in the image of S inverse F.
Since U belongs to us, it is a unit, so I can take it here 1 by U.
So what element, can you tell me the element which maps to a m by S? F of that element should be m by S. M prime by, this implies that F of sorry, S inverse f of m prime by us will be equal to f m by us, which is um by us. As an equivalence class, this is same as m by s. So this implies that m by s is in the image of S inverse of f, and that implies image S inverse f is equal to kernel S inverse G. So what we have proved is that if m prime to m double prime is an exact sequence, then the induced exact sequence S inverse m to S inverse m S inverse m prime to S inverse m to S inverse m double prime is also exact. So let S be a multiplicative set in A, let m to m double prime be an exact sequence of, so let me call this Fg, exact sequence of A modules, then the sequence S inverse m to S inverse m prime to m to S inverse m double prime. This is an exact sequence of S inverse A modules. This is exactly what we proved now.
If we are considering that S inverse A module,
Yeah.
then there u dot gn, how can we induce that inside u?
Sorry?
U dot gn equals to
G, u dot gm equal to 0. Where is this equation happening? This equation is happening in m double prime, right? M double prime in A, it's an A module. This is by definition, when an element is 0 in m by s, by definition it is this, right? And this equation is happening in the module M, and G is an A module homomorphism. That is why we can. So yeah, another important property, I think I should be able to do that today. So I have this A module, I have S inverse. There is a natural, map S inverse A cross M to S inverse M, right? A by S comma M is mapped to AM by S, okay? And by the universal property of tensor products, there is this extends to a map from S inverse A tensor M to S inverse M. So A by S tensor M is mapped to AM by S. What are the, can we expect that this is an isomorphism? Can we expect this is injective, surjective? Is it surjective? Any element here is of the form M by S.
so 1 by S tensor.
I take 1 by S tensor M is mapped to M by S. So therefore, this map is, so let me call this F prime, I call this F. F is surjective so the question is this injective? It is an onto module homomorphism, is this injective? Okay. So, let us look at first let us look at an element of S inverse A. How does any element of S inverse A look S inverse A tensor M look like? It is a linear combination of the basic tensors, right, the elementary tensors. So, if x by S is an S inverse A tensor M, then x by S is of the form summation AI by SI tensor MI, some finite combination of the form like this, right. Now, if I take this, look at this that localization, AI by SI is same as I write AI TI by S prime tensor MI. Let me explain what are S prime. S prime is the product of SI I from 1 to n, and TI is S prime by SI. See, I mean multiply and divide by the remaining SIs from S1 to Sn. Si is present here. So, I multiply and divide by and multiply both numerator and denominator by the remaining product. So, if this is, see, suppose I take 3, A1 by S1 plus A2 by S2 plus A3 by S3. What I do is I write this as S2 S3 S2 S3, here I put S1 S3, here I put S1 S3, here I put S1 S2, this S1 S2. This is same as A1 by S1 by definition of localization. So, this becomes an element of this form, sorry, AI. Now, this I can take it to the other side. This is same as summation I from 1 to n, 1 by S prime tensor AI TI MI. But here 1 by S prime is unit, this is same for all summation. So, this I can write it as 1 by S prime tensor I from 1 to n AI TI MI. So, this is some m. So, what did we show? Every element of S inverse A tensor M is of the form 1 by S tensor with some element of M. Every element of S inverse A tensor M can be represented in this manner. So, this is some element x, I should write only x here. Some element x in this is of this form. So, this implies every element of S inverse A tensor M is of the form 1 by S tensor M prime. Now, it is much more easy to handle. Suppose, so I start with, suppose some element is in the kernel, an element is in the kernel, I can take that element to be of this form. Okay. Suppose f of 1 by S tensor M is 0, that implies that M by S is 0, that implies there exists U in S such that UM is 0. Now, can you see that this is 0? 1 by S tensor M, I can write it as u by u s tensor M, u is in S. So, therefore, this is same as this. This is equal to 1 by u s tensor u m, but u m is 0, therefore, this is 0. So, this implies f is injective. So, that implies f is an isomorphism. And so, what we have proved is S inverse A tensor M is isomorphic to S inverse